The broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody, and welcome to the introduction of IBC Restraint Systems. My name is Sami Algazine. I'm the VP of Vibration Isolation and Restraint Systems with Vibroacoustics. We have another presenter today, John Giuliano of the VMC Group, that will present later. And we have Paul Meisel from Kinetics that will be answering questions. On the side, you'll see a chat, and we're going to handle the questions today by people asking questions in the chat. And at the end of the presentation and webinar, we'll leave a few minutes to be able to answer some of these questions to the public. If we don't get to your question, we have your information, and we'll try and answer your question through an email after the fact. We really appreciate everybody joining us today, and we hope you can take something from this webinar. We plan on doing more webinars in the future to be able to help with everybody in understanding the building code. Here's the agenda of the webinar today. We'll be covering what VISCMA is, who we are, what we stand for, and what our purpose is. We'll take a look at why are these restraints required. Get a better understanding of code terminology, do a little bit of a deep dive into seismic restraint requirements for HVAC systems, equipment, and distribution systems, such as piping, ductwork, and electrical. We'll talk a little bit about wind, which is one of the forgotten areas where restraints are frequently required. And then we'll look at the type of restraints that are available and their proper installation. Finally, our audience are contractors, consultants, manufacturers, and code officials. So we'll talk a little bit about the different responsibilities of each and end with some key takeaways. What are the important things to remember after the fact? So VISCMA is a collection of partners and companies to form the Vibration Isolation and Seismic Control Manufacturers Association. We were incorporated in 1999. And we're experts in the field of seismic restraint, wind restraint, vibration isolation, and noise isolation. Our purpose is to work together as a collective of professionals with a lot of knowledge and a lot of experience and expertise to be able to provide resources, interpretations, and standards, as well as best practices for the design professionals, installing contractors, and code officials in our industry, to be able to maneuver through the different documents that are necessary to understand what needs to be done for a building when it comes to vibration isolation and seismic restraints. So to kick off our agenda today, we'll take a look at when are these restraints required. We've had a lot of communication with contractors, code officials, and specifying engineers to say, okay, I have a building, sometimes it requires seismic, sometimes it doesn't. Just to start off, we need to be speaking the same language. What are we talking about? When we talk about restraint, we're talking about the restraints of non-structural components. In our industry, generally, these are mechanical and electrical equipment and distribution systems, usually within the HVAC world. And what we're trying to do is restrain them against forces caused by extreme events, not just earthquakes, but also winds, bomb blasts, and different things that can happen to want to move these pieces of equipment. The main purpose that we do this is for life safety. In different buildings, you have these pieces of equipment, and you want to make sure that they're operable during and after an event for life safety purposes. You also don't want these heavy pieces of equipment or these heavy systems falling on people, creating bodily harm. So we have a few different codes and references that we work with. The main is the International Building Code, also known as the IBC, which references the American Society of Civil Engineers, number 7, that is updated, and the number afterwards, 02, 05, 10, is the year that it is updated. You have government reasons, like the UFC, which is the Unified Facilities Criteria that's used for government buildings as well as military buildings, for mission-critical components, for anti-terrorism and Department of Defense. And then the last reason is due to the owner's request. Sometimes for insurance purposes, to be able to get a certain level of insurance, or to be able to protect very important data. A lot of restraints are put into data centers, for example. Okay, let's talk a little bit about code references. So there's the code, there are standards, and then there are guidelines. An example of the code would be the International Building Code, or IBC. An example of a standard would be the American Society of Civil Engineers, or other standards that are available. And then guidelines or interpretations would be something similar to the VISCMA 412 manual that shows how to correctly install seismic restraints for mechanical components. Translated, the IBC in the code really signifies the requirements. The standard tells you how to do it and provides you with the formulas necessary that you have to go through. And then these are always up to interpretation. And the guidelines serve as a good interpretation for the people that have to do the work on how it should be done. A different slice or a different way to look at this is that there's a legal requirement and a non-legal requirement. The legal requirement is the code that becomes part of the building code, and then the standards that are also referenced by that code. The non-legal aspect are the standards that exist that are not referenced in the code itself, or the guidelines of the commentary that come with it. And again, an example for you to see would be the VISCMA 412 manual. Since 2003, the IBC has been referencing the ASCE, American Society of Civil Engineers, for the minimum design loads for seismic and wind. IBC is updated every 3 years. It was the amalgamation of different building codes from across the United States to create the International Building Code. And every 3 years it's updated. It's adopted by different municipalities and jurisdictions at different times. We still have people that are on IBC 2009, and we will have early adopters of IBC 2018 in early days of 2018. And there can be local amendments for each of these municipalities. The ASCE document is updated as needed. It was updated in 2005, 2010, and 2016. And you can see that each IBC code references an ASCE 7. So in 2018, when your jurisdiction adopts that code, it will reference the newly updated ASCE 716. These are the critical documents necessary to have an understanding of what the requirements are for any new construction or retrofit construction in your area. Let's talk a little bit about seismic, and we'll start with a little bit of trivia. We've taken some information from the USGS website, and we've taken an average week. So if you were to think to yourself, how many earthquakes occur in the United States in any given week? I'll give you a little bit of time to think about this and come up with an answer. We ask this question when we do these presentations for different influencers. Usually the answer is 5 or 10, or maybe some people would guess that there's 20 or 30 in a given week. The answer for any average week is over 1,200 earthquakes. And then you can see here on a map of the United States, there's a lot located in Alaska, California, up the West Coast, but it isn't only limited to those areas. You can see that in Montana and Idaho, Oklahoma, Tennessee, and usually in a given week, Hawaii, South and North Carolina would have some seismic activity as well. So this is not just something that appeals only to the West Coast. IBC terminology. There are a few different pieces of terminology that are important to remember. The structural engineer of record has responsibility for figuring out the classifications that are on the left of the slide. First, we'll talk about the occupancy/risk category. What type of building is it? And the importance of that building. 1 would be a farm or a barn, and 4 would be an essential facility such as a hospital, 911 call center, or a police station, with varying degrees in between. Obviously, you could see after an extreme event or during an extreme event, it's far more important for the structural integrity for both the building and the non-structural components for higher risk category buildings. This then determines a building importance factor, which is not to be mixed with a component importance factor that we'll speak about in a moment. The site class is a classification of what the building is being built on. What's it sitting on? Bedrock or a swamp? And the seismic forces will act differently on the building and its contents depending on that site class. Then there are short period response accelerations or ground motions known as SDS and SD1, and these are determined by the location or zip code and are based on history and intensity. A structural engineer of record would take those 4 components plus other factors to determine the most important category that you need to remember from this webinar today, and that is the seismic design category. The seismic design category gives you a classification of a building and advises the consulting and design group of the needs and requirements necessary for restraints of non-structural components within that building. And we'll cover what A to F means in a moment. Yes, the people at the building code are trying to confuse you because it's the same classification, A to F, as site class. So don't get confused between those, and don't get confused between the difference between a building importance factor and a component importance factor. The last element for the structural engineer to determine is the wind design speed and exposure category. All of this information that we're speaking about usually can be found on page 1 of the structural notes S1. Now, the MEP engineer of record, mechanical, electrical, plumbing, does have a very important role. Only he or she can determine which components are important for the continued operation of that building. And this is the component importance factor. It can only have 2 classifications, a 1.0, which is standard, or a 1.5, which is life safety or some other elements that we will cover in one of the coming slides. Basically, the component or system is important to the functioning of the building and life safety, or it's not. And this needs to be done on an individual system or equipment level and shouldn't just be a bland, broad brush across all systems within a building. By doing that, there might be overkill with regards to restraining things that don't need to be restrained. So when we take a look at the seismic design category that goes from A to F, for buildings that are classified as A or B, there's no seismic design requirements for non-structural components. There are absolutely requirements for the building itself, but when it comes to restraining non-structural components, there's nothing that we need to be worried about or to take a look at. For buildings that have a seismic design category of C, only the systems with an I sub P of 1.5, which we will show you how to determine that in a moment, require restraints. And then there are exceptions. For buildings that are D, E, or F, usually you'll only see C or D. E or F are more of the extreme. But for buildings that are D, E, or F, all of the MEP systems, both 1.0 and 1.5, will require restraints. However, there are some exceptions and some exemptions from this that we will cover. Here, what we have done is we've referenced the ASCE 710, since that's the most commonly used version of the ASCE currently, Chapter 13. And it's Section 13.1.3, showing mechanical engineers of record, or MEP engineers of record, how to determine the component importance factor for different pieces of equipment and different systems. And here are the 4 categories that makes the I sub P 1.5. By making the I sub P 1.5, you're there's more likelihood that that piece of equipment will need to be restrained. So you can see, I'll cover a couple of these. The component is required to function for life safety purposes after an earthquake, including fire protection sprinkler systems and egress stairways. Or the component conveys, supports, or otherwise contains toxic or highly toxic or explosive substances. So you can get the picture, and if you reference the ASCE 710, Chapter 13, you will find these requirements of where you should classify a component as 1.5 versus 1.0. Let's take a look at some of the restraint requirements for piping, duct, and equipment. Here you can see a few tables showing the exemptions and the requirements for different seismic design categories for different pipe diameters. You see the pipe diameters on the left going from less than 1 inch to greater than 4 inch. You can see for both 1.0 and 1.5 component importance factors for seismic design categories of A and B, the first column, that they're all exempt. And then when you move to seismic design category C, you see that all 1.0 is exempt, and the requirement for 1.5 is anything that is 2.5 inches or larger. And now you can see why the role of the MEP is so important. If you classified everything as 1.5, then anything over 2.5 inches would need to be restrained. And you could have very varying scopes of supply for that building. For SDCs of E, D, E, and F, you can see that there's still a requirement for 1.0, anything that's 3.5 inches or larger. I'd love for someone to show me some 3.5 inch pipe, never seen one. And then for anything that's 1.25 inches and larger, for 1.5, you'll have a requirement to restrain. Duct is a little more simple. You need to find the cross-sectional area, the equivalent cross-sectional area of being less than 6 square feet. It's exempt across the board, and larger than 6 square feet, it's required in seismic design category C buildings with a component factor of 1.5, or for seismic design category D, E, and F for both 1.0 and 1.5. There is also another rule that these are the best guidelines, that if you trapeze smaller pipes together, you might trapeze a whole bunch of 2-inch pipes on a seismic design category D building that you would think are exempt, but if it becomes more than 10 pounds per linear foot, you need to restrain it. So any contractors that are listening, there are some strategies obviously that can be done. You might not want to trapeze smaller pipes together to reduce your seismic scope. The same thing applies for duct, so you need to be careful with regards to double wall duct or thicker gauge duct work that passes the weight requirement. Let's take a look at equipment. There's a few different exemptions based on weight for equipment. Basically anything under 20 pounds, which is not too much in the non-structural component world, then you're exempt. If it has less than 20 pounds, it's not considered to have life-threatening aspects. 75 pounds, if it's rigidly connected with no flex and has an operating weight of 75 pounds or less, and you see this with some VAV boxes, then there's an exemption. And then usually for ground-mounted, floor-mounted equipment, there's a 400-pound rule, but it has a few different factors. This is only for ISOPs of 1.0. They have to be mounted 4 feet or less above the floor, so usually they're connected down to the ground. They have to have flex connectors on the attached components, and obviously have an operating weight of less than 400 pounds. Now, for a different code, for the UFC, there's the 31-pound exception, which basically says anything that's under 31 pounds is exempt. coming to an end of my part of the presentation before I pass it off to John Giuliano. We'll quickly just take a look at a couple of types of restraints. We've spoken a lot about requirements, but we haven't taken a look at what these look like. So a restraint is anything that would restrict movement in a certain direction. That's the definition of what a restraint is. And these could be cable restraints that are usually used for distributed systems and suspended equipment, rigid restraints, which would be brackets with a piece of strut or angle in between that would work as a two-way restraint for distributed systems and suspended equipment. Steel-housed isolators, so an isolator like you see here in the middle that has a housing around it. The isolator allows small movement for vibration isolation, but under any event, the housing strength will kick in and basically stop the equipment from moving. Snubbers and brackets that maybe are put around a piece of an air handling unit or a piece of equipment to stop it from moving. And then you have different types of structural stands for ductwork, piping, and tanks, as well as anchors that would just go through the feet of plate and frame heat exchangers, different bolts and screws. This final category has to be ICC approved. You can't simply take any anchor off the shelf and install it. It has to be an ICC approved anchor, bolt, or screw to be put in with the equipment and mounting holes. So I'll just leave you with one thing with regards to the equipment and the product that you use. It must be included in the submittals and stamped by a professional engineer. For example, you can't just select something, put it on and say, okay, I put a snubber around this air handling unit. The design must be calculated so that an engineer of record can determine that the seismic restraint that is being used is sufficient to withstand the forces. Since the forces vary by location to location, floor to floor, equipment to equipment, a calculation needs to be done to ensure that the restraint can overcome those forces. And lastly, the product should be tested as per the industry test method to ensure that it's the load envelope that's being provided by the manufacturer is accurate and does what it says it would do. And this is a newly established standard by ASHRAE, and it's standard 171. Okay, that ends the first part of our webinar. I will be passing off controls to John Giuliano, and he will take it from there.
Okay, thank you, Sammy. Can you hear me, Sammy?
Yes, I can.
Okay, so presumably everyone else can. Let me just steal this from you. And you guys may be seeing during this my pull-down menu. We were having technical difficulties, so you'll be seeing my pull-down menu, but hopefully nothing else of my screen. And thank you, Sammy. That was a lot of continuous talking, and without feedback is difficult. And I'm going to go through this just a little slower, hopefully, so we figured we had 90 minutes, but we left time at the end for questions and answers, which I hope we have a bunch of. All right, so now, as Sammy kind of went through, hold on a second, let me get to where he was. You were there. All right, so now going through the process he went through, you've determined, at least thanks to the MEP engineer specifying which is IP 1.5 and such, you now know what you're going to have to restrain. And so what you have to try to then determine is, how do you go about determining where to put restraint locations, how often, how strong and such. So in general, we start with we look at industry standards, and SMACNA is one that we typically use. Generally, if it is a third party, it's a sheet metal organization, but they've been doing for many years a lot of seismic testing, seismic analysis, and they've effectively created an industry standard of what we call a 2040 or a 4080. And for low deformability piping that's typically brittle, cast iron and such, you want a transverse restraint every 20 feet on center and a longitudinal every 40 feet. And in general, you look at your piping drawings in plan view, and you start at the beginning of a run and you measure out 20 feet and you put a transverse brace. And every other one you would put a longitudinal restraint. And longitudinal being inline to the pipe, transverse being perpendicular. On standard piping, standard black iron piping, which we call high deformability, which is more ductile, go to a 40-80 restraint locations, and that's 40 feet downstream and 80 feet across. And now, I just got somebody saying that they're looking at slide 12, but I'm looking at slide 21. Sammy, you want to speak up and let me know? What do you see?
It's moved on to 21 now. It was slide 12 for a while, but now it seems to be on the right slide. You're good to go.
Okay, I apologize for that. It was 21 on my screen. All right, so I guess you'll have to see the sidebar. We're still having some technical issues. All right, so now the note at the bottom is very important, because if you have a run that's shorter than this spacing of 20, 40, or 40, 80, you still are required to put two transverse restraints. It prevents just global rotation of the piping run, putting a transverse at each end. One longitudinal is still functional in this case, because as we know, you can slide a force along its line of action and you won't have an issue. You don't create a moment. So that's to prevent the global rotation of that piping run. So you put one at each end. And here, just from a schematic point of view of the type of details you'll see on a submittal or see on the MEP types of drawings, and they're broken up fairly simply. A transverse is, just as it says, you'll have two cables, two rigid braces, two structurally designed restraint elements off at a perpendicular to the run of the pipe. It's shown in the 3D, and it's also shown in plan view, where you just put a bar across the piping run and you're calling out for a transverse, or sometimes it's called a two-way. The next one is the longitudinal, as very much well it describes, just it's a straight line. You can grab either end of the clevis bolt, or you can grab the base of the hanger rod. And what's shown on here is also very important. I know Sammy had on other pictures, these rod stiffeners and clips when required. When you do the math, as Sammy had gone through to, I guess we didn't get into that level of detail. When you do the math to determine the seismic force being applied, since the seismic force is a shear force, when these cables or these rigid braces pull back that pipe in tension, it has a component in the vertical direction which will compress that hanger rod. And more often than not, that's a relatively thin rod with a very long length. And under that compression load, it will typically buckle. So most of the drawings, when done correctly, will have a rod stiffener of some means to prevent buckling of that hanger rod. And that's shown in all four of these drawings. The next one is a combination where you can put, what's shown there is two 45s, which that would take care of a one-way transverse and a one-way longitudinal. It could be also a 090, performing the same function. You just rotate those two 45 degrees around the vertical axis. And the one in the lower corner, which we apologize for putting a slightly different drawing in there, it's showing how to connect a four-way brace, which is the two transverse braces, one in each direction, and the two longitudinal. Now, it's important to know that Sammy mentioned the cable and the rigid bracing. When it's cable, as we know, cables can only take tension. You can't push on a rope. So a transverse would require two cables. You can also design this restraint for a rigid brace that only technically can be in one direction off of the pipe, but it has to be designed for the compression load. So it'll take the tension load relatively easily, regardless of the length, But once that brace is too long, you have to check the buckling of it. So when you go for rigid bracing, you can put one, but depending on the load, you do got to check for compression buckling. Now, did that slide move along, Sammy? If you're still there. Hopefully it has. Now, on ductwork, we use a different standard. We use a 3060. All elements of what we had done on the piping is the same. We go through the math, determine the load, determine the required capacity of the brace that we're going to apply. And the same thing, each run requires 2 transverse restraints and 1 longitudinal. And in the code, there are standards as to what defines a run. If it's a typical bend or such, some of it may be small enough where it is not a run. And then inline equipment, 75 pounds and less can be restrained when it's rigidly attached to the ductwork. Anything over it has to be independent. The assumption there is something weighing 75 pounds or less, the standard design and construction of the duct will restrain and support that 75-pound piece of equipment. And here's the same 4 layouts as for the piping before. And so rather than go individually through them, one thing I do want to point out that's important, a lot of people don't realize, if you look, probably that's best on the lower 2 drawings, the transverse bracing doesn't technically have to span outboard of the ductwork. They can cross inboard, so they don't run into other pipes, other ductwork. You still run it at the same roughly 45 degrees off the horizontal, and you have a lot easier installation. So for the contractors out there, you may only see them on the drawing where they splay outboard, but you can go inboard if you have the room. Much less interference. All else has to be equal, the same. The math has to be done right. It still has to have the rod stiffeners, and the anchors, as Sammy said, have some kind of third party. He referenced ICC, which generally the one is out there, but there are other third party certifiers for anchors. So to get the allowables from there when you do the math for that one. And it's a very important note at the bottom. Non-rated friction beam clamps are not allowed. The code is explicit that you're not allowed to use friction due to gravity as a seismic restraint. So here's that discussion of rod stiffeners I was bringing up. In general, you're going to see any rods from 3/8 to 1 1/4. Occasionally you will get higher, but those are the general 90-10 rule you're going to see on your job sites. And that table shows the maximum length before you're going to need a stiffener. And so you see a 1/2-inch rod, anything over 2 feet, it's going to require stiffening, because any compression load, it's going to buckle. It almost buckles under its own weight when you stand it up vertically. And then when you have it with an isolator, that sketch shows that you are now technically using that hanger box as part of your compression system to get that compression load back up to the building. And as such, you're going to need to install, and it's typically on all of the manufacturer's submittal drawings, install a stop washer with a nut underneath the box, so when you push on the rod, it just doesn't go through the box. And this way you can carry your compression load, and those boxes are typically designed for that, since they're also designed, at least on the tension side, for large safety factor over their standard spring capacity. And the notes on that table are also important. A minimum 2 rod stiffener clamps. It's rare, but occasionally you'll see just one piece of angle bolted to the side of that rod that doesn't shorten the effective length of the rod. The purpose of those stiffening clamps and attachments is to effectively shorten the unsupported length of the rod. So when you do your buckling calculation, depending on your variables, typically like an L sub U, you can now use it at what's shown in that drawing, to say a 24-inch instead of the full length of the rod, which dramatically increases your buckling allowable on these rods. Now, where do they need to be installed? They being seismic anchorage and such. right now we've been talking mainly about overhead suspended equipment, but the same process of going through the calculations, going through the requirements, going through the seismic design category to determine what needs to be anchored. Then now you've determined that this equipment is floor mounted and needs to be anchored. You have to go through the calculation to determine the load on each anchor, and then use the appropriately rated anchors. And Sammy put together this PowerPoint, so he did all the heavy lifting for us. Thank you, Sammy, again. And he pointed out 4 of the manufacturers that are typically out there. We know there are others, and this does not say that these are the only ones to be used, but we do know there are rated allowables out there. They've done testing, and most contractors easily have access to these manufacturers. But the math still needs to be done. Someone has to go through the numbers. An engineer has to do his calculations, put a stamp on it, that he followed all the code requirements for amplifying the loads or putting safety factors onto the loads when you're attaching this equipment to concrete. So for the reviewing engineers, if there's any on the call, you do want to make sure that the calculation included all of the necessary safety factors that ACI and ASCE call out, because they're generally in there more for the installation of these anchors because it is so varied. We all know that, that the safety factors are there for a reason, so you just need to keep an eye out for them. And that reference to the ICCES, that's where the approved ratings for these anchors would be found. And the documents that ICC put out for these anchors, they also do the math and go through it for you, through the calculations. So even just going to that website to pull out a few of these reports, you'll learn a little bit about the analysis and installation of anchorage. Wind restraints. This is a good year for this one. We probably haven't updated this. We got to double check, but as Sammy said, there was some trivia. If you ask yourself what was the costliest natural disaster in U.S. history, it was Hurricane Katrina. Well, obviously more than just wind damage, but there was $108 billion in damage, and we know there was way too many, 1,833 people too many were killed because of it. And this year we know between Texas and Puerto Rico and other locations, there's been wind damage all over the place. And one of the issues we know is the attachments, which we'll get to. But other than seismic, ASCE 7 puts out maps for wind. And as luck would have it in our country, most of the regions that are high in wind are low in seismic. So somewhere or other, regardless of where you are, you're going to have some kind of requirement that's going to require restraints, analysis, and such to keep mechanical equipment attached to the building structure. Here, the map here is just showing more of an occurrence of hurricanes throughout 100-year map history. We all know where they come in, and you see Puerto Rico is red. They're still out of power. Their infrastructure and the equipment was not all done properly, so now they're paying the bill for bad designs throughout the years, which hopefully with the IBC and the training, that all gets fixed eventually. So IBC, they have maps within the code, which they have changed through the years, and that's why they're broken out in 2006, 2009. There was one way to calculate the loads based upon wind speeds. There was a wind factor of 1.6 in the load combinations in these building codes. So if it's very important when you're doing the analysis for wind that you're looking at the right map relative to the right code that you're using. Because now when we move on to the 2012 map, it looks like some of the wind loads may have gone down for the higher buildings, but they really haven't. It's more that the amplification went from 1.6 to 1.0. So actually, no, the wind loads went up. Apologize for that. It was the other way around. We went to from a 1.6 to a 1.0 amplification, but the wind speeds went up. So effectively, the wind pressures, in general, they roughly remained the same, though if you notice on the 2012 maps, there's multiple maps, and it's based upon, if you can see my mouse over here, risk category now. And Sammy mentioned that earlier, that that's an important piece of information we need from the engineer as to the type of building. And on the S001, it should be there. And as you go up in risk category, for obvious reasons, the designed wind speed goes up. And so if you're using a 2012 map, you need to use the 2012 load combination factor to get the correct pressures. If you're using the 2006, 2009, the wind speeds are a little bit lower, but you have a higher amplification. So you need to be very sure of your risk category and the code you're using. Now, in general, though, through the years, the wind code equation stayed roughly the same. And in 705, it was in chapter 6. I'll get there later. In 710, 716, it moved to other chapters. And for mechanical equipment, which we're discussing, you'll find all of the details in chapter 29 for ASC 710 and 716. But effectively, from your wind speed, you have to determine a pressure. There's gust effect and force coefficient factors that need to be put in. Though in general, for the equipment we're dealing with, we're not designing buildings. We're talking about mechanical equipment, rooftop equipment, rooftop structures. What's highlighted in yellow is there's a 1.9 factor. And in the newer codes, which generally is everybody's been using, that QC combination becomes a 1.9. And then that's multiplied by the frontal area of the equipment, which is the area of the equipment normal to the wind, which will be receiving the load. Now, here are some examples of what happens when it's done wrong. And I don't remember where some of these are from, but I do know the one on the lower left was from Sandy. The other bad designs, I don't know exactly which hurricane or windstorms they came from, but needless to say, they were done wrong. The equipment itself wasn't attached properly to the building structure. Very similar to the suspended equipment and the floor-mounted equipment, roof-mounted equipment needs to be attached to the building structure using the equations calculated here to determine the type of restraint or anchorage to the building. Here's just some more pictures of what can go wrong. This one in the upper right actually came from ASHRAE. ASHRAE had a couple years back in ASHRAE Journal, had a big article on wind loads and showing what happens. Needless to say, luckily nobody got hurt, but if that was your truck and your car, you had a tough day that day. And once again, the equipment in the upper right and the lower right wasn't attached properly, and I believe that sketch of that little bracket was trying to hold down that big piece of equipment that went for a ride. Obviously improper designs. No one went through the force equations. No one went through the maps to determine how these things were supposed to be restrained. Now we have a section here on responsibilities. Sammy mentioned some of the more important ones earlier on. The most important, at least from our aspect, is the ISA-P of the equipment, which comes from the MEP. And as he mentioned, and I'm sure somebody will ask, and we can ask again, there's only two values of ISA-P available. It has a short menu. You get 1.0 or 1.5. And that determines exemptions or whether or not the equipment needs to be anchored properly. Now, the contractors, it's their responsibility to install the restraint as per the manufacturer's instructions. The manufacturer will be submitting his equipment with the calculations showing that this is the means of doing it. And so the engineer has reviewed it, so by the time it gets to the contractor, that is what needs to be done. And it is his responsibility to ask questions. No engineer has put out the perfect drawing ever, and as an engineer, I'll admit to that. So there will be something missing, there will be something unclear, and it's a responsibility of that contractor to ask that question. It's always safer to ask the question than do it wrong and pay for it afterwards. And it's his responsibility to use the product provided or specified and approved by the engineer. Going to Home Depot is not the solution. If the manufacturer provided it, there's a reason they're providing it. It was tested, it was approved with their equipment. The consultants, they get in obviously on the job a lot earlier, and it's their responsibility to write a project-specific specification, and they have to reference explicitly which code is the design code for that particular building. And every state varies, as we know, whether it was submittal date for permit or approval date or whatever it may be. So as an MEP, installing contractor or someone in supplying equipment, we don't know when all the paperwork started on the project. So the consultant has to put it somewhere clearly, which is the building code of the basis of design. They need to create the schedule or specify the IP, as we were talking about. Without that, as engineers, we have to make worst case assumptions. A standard of care has to be provided. We have to assume worst case if we're not told otherwise. So it gets very expensive for the building owner if that IP is not properly specified or if it's not specified at all. And the consultant also has to require the contract to submit the restraints and calculations for all projects that require it for approval, so that someone else has reviewed it, that the building engineer, whoever, structural engineer, or their consultants have looked at it and also have been at least alerted of the loads that this equipment is going to apply to their structure. Many times, especially we see some of these pictures, big pieces of equipment, very often the building engineer was unaware of the level of load that his building will see from that wind. So by submitting all of that information back up the food chain, everyone will be aware of the loads that will be applied to that building. Now the manufacturers, this actually falls under two types of manufacturers. The manufacturer of the equipment may not always be the net manufacturer of the restraint, but we all have the same responsibility. The products need to be tested in some way, shape, or form to ensure and prove that the rated loads that are being put out there have some basis. Just the old days of just saying this, of throwing a calculation and saying this is good for 1,000 pounds, engineers today are expecting more and demand more. And so the responsibility to test your product to make sure it's compliant. Also, if it's the equipment in IP, in critical facilities and essential facilities, the building code now requires the equipment to be tested anyway to show functionality after the event. We, at the manufacturers, and as VISCMA, we are manufacturers, we are required to follow the code for all calculations. And the codes are very explicitly spelled out on how to do the math, and we have to follow them explicitly and put our PE stamp on those calculations. Then we are also required to give instructions to make them as clear as possible for the contractor so he doesn't make a mistake. And like I say, occasionally we will leave something out, and it's incumbent upon him to question us and make sure he's got it right, and we have provided as much detail as possible so it's not installed wrong. Now, as Sammy mentioned, VISCMA, we've been around since 1999. I'm actually a founding member, been around it since 1999. We do provide a lot of information in terms of questions and answers. There's a FAQ page. We've produced all kinds of calculation documents, installation documents, and other documents, opinion papers relative to the code, and it all can be found at VISCMA.com. And as you see, that's the website. And Sammy, you can, if you are still there, you can take back the presenting, and thank you all for listening.
Thank you, John. Appreciate it. You know, John's got a wealth of knowledge as well as a lot of the other VISCMA members, and that's what makes the organization so valuable to help provide interpretation. So we would like to thank everybody at this time for joining us. I think Paul Meisel has been actively working with the questions and answering people's questions. We have recorded this webinar, and the recording is available. So if you respond to the invite that was sent and request a copy of the recording, it will be provided to you. Thank you very much, and please stay tuned to future webinars. We are hoping to do more in 2018 on different topics to help with the understanding of the building code and also move on to vibration isolation. Thank you very much, and have a great day.